Okay, let's get started then. So first of all, I'd like to welcome everyone for joining us over the next 2 hours or so to listen to a series of talks where we're exploring the intersection between space technology and quantum technology. So this is the fourth edition of the QTX workshop, and the first time we're actually having it virtually all online. And QTX is actually sort of a brainchild, between Markus Krutzik at Humboldt-University and my group here at NUS, where we are both, exploring how to put quantum systems into space. And we thought that it would be actually kind of nice to have a very, small and focused workshop to bring everyone together who's interested in some of these technologies. And so today we have actually an interesting, selection of speakers. And what we'll do is we'll typically divide the session into two halves. And the first half, there's a focus on communication. And the second half, there's more about, quantum memories and quantum sensors. But what we'll do is we'll have the speakers run through their talks 20 minutes each. And then at the end, if you could hold your questions until the end, we can have sort of a panel discussion where we can actually have everyone, answering questions at the same time. And so that's how we're going to play the QTX session today. So I'd like to invite Markus to say a few words as well.
Yeah, welcome everybody. Thank you, Alex. As you said, it's the first, let's say, version of a virtual QTX we have. So I remember, back in the days a couple of years ago when we first met and started to think about this, which basically was initialized by a joint funding program between NUS and Humboldt. So we will hear also later on about some of the recent results of one of our projects. So I'm very excited to. Yeah, and I'm very happy that we are, 54 people already here, and the number is still rising. We have globe-spanning speakers, so I'm also grateful to everybody who joins us, especially for the guys who are on a late hour. And yeah, thank you, Alex, to you and your team for organizing this, and I'm looking forward to our talks.
Okay, thanks, Markus. So our first speaker will be Chithrabhanu Perumangatt. He's actually a research fellow working inside my team. And he's going to present some of the latest results we have about how we are validating our next generation of entangled photons light sources for quantum communication with a satellite. So Chitra, when you're ready, you can take it away.
Yep, thank you, Alex. Let me share my screen. I hope everyone can see my screen.
Yes.
Right, cool. First of all, I would like to thank the organizers for inviting me for QTX. I hope next year we can meet in person. So my name is Chithrabhanu Perumangatt. I'm from Center for Quantum Technologies, National University of Singapore. My topic today is tabletop demonstration of satellite to ground quantum key distribution. As mentioned by Alex, our group is focused on how to enable quantum communication between satellite and different places on Earth. So this is one of the experiments which we have done in the lab, not in the satellite, to validate some of the assumptions and to see how our system performs under such high losses, like a satellite to ground link. So before going to the experimental details and the results, I would like to motivate everyone for the satellite-based quantum communication. Okay, so generally the communication, the classical communication is done over fiber, right? So the fiber has been there for years now. So it's natural to think of fiber as a medium for quantum communication as well. But the problem is that there are hardly any candidate for quantum repeaters. So the losses plays an important role, how far you can communicate using a quantum signal, because these are very weak. Under losses, it will have deep coherence and it will have less efficiency for communication. So if you see a distance versus loss curve for fiber and a satellite, you can immediately say satellite wins hands down. So that's why the main motivation towards putting these systems on a satellite. And moreover, if you have these systems on a satellite, you can communicate to different parts of the world. So if you consider this satellite to be a trusted node, you can have communication between two different countries, different continents. And if on further, if you have constellations of such satellites, you can have a global coverage for quantum communication. There are multiple designs or ways you can do this. You can send this quantum signal from a satellite to the ground station, or ground station to satellite, or distribute entangled photons between two ground stations, or communicate between two satellites using quantum channel. If you are more interested, you can check out these papers. Okay, so now I'm coming to the system what we are planning to develop, or we are already doing the development. Oh, sorry. Okay, so this is the main architecture for our entanglement-based quantum key distribution from satellite to ground. So this is the satellite, or Alice, and the ground, which is Bob. So our main quantum resource is nothing but an entangled photon source. So it's a pair of photons that are entangled in polarization. So one of the photons is detected within the satellite itself, and the other photons is transmitted through a telescope. And now the ground station, it also has a telescope, and it receives this signal, and this is detected on this similar type of detection setup. So once this is detected, it generates timestamps, and you can get the coincidence between this satellite and the ground station. So the entanglement exists only if you have two pairs of particles, right? You have to detect pair one here, the particle one here, and then the particle one has to be detected here. So but this channel is very lossy, so we want to mimic this loss in our lab. That's why we are going for this tabletop demonstration. So once we generate these tags, you have to have a classical communication for error correction and privacy amplification. Okay, so I want to define some of the parameters, or some of the words I will be using. The first bit is QBER. This is quantum bit error rate. This is coming from the source and the noise on the detectors. Next is efficiency. Efficiency is nothing but the coincidence counts divided by the single count. So for a given single counts, how many coincidences you will get. This is also a function of loss. If you have more losses, you will have less coincidence per single counts. Another thing is accidental coincidence, and this is the coincidence what we don't want. So if you have two detectors detecting two singles of S1 and S2, this is the detection rates, and you have a coincidence window of tau, this is your accidental coincidence, and this actually increases your quantum bit error rate. Another word is shifted key, and this is the key, the key before any error correction. So this key includes all the errors. But if you have shifted key and a QBER, you can do the quantum the error correction protocols, and then you can finally get the secret key. Now generally this is enough, and generally you can have infinite amount of secret key, but this is not possible in a realistic scenario. The secret key length is finite, so you need to have account for this finite effects. So you have to have the finite analysis for the security. You can refer this paper for this one, and once you have done this analysis, you can do some privacy amplification. You can get the finite key as well. So this is the main parameters I want to mention, and this is why we are doing this tabletop demonstration. So the first is that, okay, we want to get these things done. So we want to check whether our design and our components works, and it fulfills the requirements of our mission. And next is that we construct a model for a given input parameters. We construct a model how much the system should perform under loss. So we want to validate this one. We want to validate the optical components, software stack, And also we want to estimate some of the margins and requirements. I will come to these points later. So this is the Q-rate model, or the Q-rate model is nothing but a performance of system under loss. So you have some input parameters such as how much entangled photon pairs you are generating, how much is your Q-bar introduced by the source. So the source is an entangled photon source, but it's not ideal source. So you have some you have some imperfections at source as well. Also, how much is your efficiency? This depends upon your link, your source coupling efficiency, your detection efficiency, and all the losses in the system. Also, you have detectors, dead time, and time stamping. So you give this input parameters, and finally, for different losses, what you get is the quantum bit error rate, final quantum bit error rate, and how much coincidence that is survived through the loss. And from there, you can get the shifted key. Once you have these two, you can have secret keys. It can be with asymptotic assumption or the finite key assumption. Okay, so this is some of the basic requirements that we have fixed from our group. So we want to have at least 25 million pairs generated, and we want to have an end-to-end efficiency without loss 20%. That means from the source to the detectors, the total efficiency without any additional components should be 20%. The intrinsic polarization visibility has to be 95% or more. Q-bar for the source should be 2.5. Q-bar for at 30 dB should be less than 5%. And the secret key, this is an estimation. Secret key has to be at least 100 to 200 bits per second. Now you have these input parameters. You put these things into the model. Also, you have to define what is your dark count in Bob. Dark count in Alice is not so relevant because Alice has a lot of detections, but because there is no loss in the Alice photon, but Bob photon has a lot of loss. That's why this is important. Detected at the time, coincidence window. So this is how you can get a trend of secret key versus link efficiency. Also, you can have a trend of Q-bar versus link efficiency. Now we have the model. Now we need to do the experiment. So I'll not be explaining much about it, but this is a source. If you are interested how to make this kind of entangled photon source, this is high performing entangled photon source. You can check out this paper. We couple this entangled photon source into a single mode fiber. This is generated using a spontaneous parametric down conversion. And we couple this into a single mode fiber, and after polarization correction, we split the signal and idler because these are two different wavelengths. Using a dichroic mirror, the idler goes to Alice, signal goes to Bob, and you have variable loss in between, and that's how we introduce the channel losses. So this is the initial results. I want to just mention this curve you see, the black and blue curves. These are not the fit. These are the model that we have. That means we have these input parameters. So we operate this source at very low rate. We measure its Q-bar, we measure its efficiency. Also, we input the parameters such as coincidence window, the rates that at which we are going to operate, and we construct this model here. And once we construct this model and we do the experiment, and we just plot this model along with the experiment, and this you can see that this agrees very well. The singles in the Bob, this is the Bob singles. That means this is the ground station single, will reduce with the loss. This is expected, and Alice singles are a constant because there is no loss. The coincidences also decreases. This is the model, and this is the experimental values. Okay, so we have these coincidences. Once we have the coincidences, what we can do is that we can have the shifted key. We can create a shifted key from the coincidences once you reveal the basis, and you can estimate how much is the quantum bit error rate. That means how much is how much bits are error have these errors. So this quantum bit error rates increase with the loss. This is the model, and this is the experiment. Again, fits reasonably well. And this is because when you have more loss, the background counts or dark counts in the detector in the bob takes over, and that introduces more less signal to noise ratio. So that's why you have more cuber, and the secret key it's also a function of the how much is your shifted key and the cuber, and it reduces with the loss. So again, here we can validate our performance with the Ling model. Or we can validate our Ling model with our experimental performance. So we have done the validation. Now we want to see what are the margins we have, or what are the parameters we can choose so that we can get a safe position for the key rate. So this is one of the thing is the effect of background. So here background is only for the bob, that means the ground station. So we start with the per detector. This background includes the background light and the dark counts of the detectors. So this increased from 200, 350, and 500 or 1000. This is per detectors. So what we do in lab is that we just remove the curtains such that this is no longer really dark, and we increase the background here. So when you increase the background, you can see that the secret key at high losses are less, and at high background rate, you can see that after 37 dB or so, we don't have a positive secret key. So this is in kilobits per second, and this is logarithmic scale as well. So this is important because this gives us we can give some requirements for our electronic engineers. Okay, we need the detectors has to be this good in terms of background. And also when you design a ground station, the field of view of the ground station determines how much is the background radiation from the atmosphere. So that also we can define using this analysis. So this was really useful to do this kind of analysis. Another trade-off here is the rates. We can actually in fact increase the rates. Only the limitation is the detectors. Probably if you have a detector which is limited and also timestamp which has limited number of tags per second, that is the only thing limiting us. In principle, we can go to very high generated count rates. So this is the model and this is the results. So we change the generated pair rate and we get the secret key for different coincidence windows. So we find that if you go to higher and higher count rates, we have to optimize our coincidence window to be shorter and shorter. And this is also important because while operating, we can choose dynamically what is the generated pair rate, and in software we can choose whatever coincidence window what we need. Okay, so that's it. Okay, so just some comparison for the performance. So this was the one we wanted, and of course our performance is much higher than that. This is our baseline. We can go up to 50 million pairs per second. We can actually even go higher. Only our detection system and the timestamp limits us. Another thing is that end-to-end efficiency without loss. We can get up to 25%, and the intrinsic polarization visibility is also higher, and QBER, quantum bit error rate, is less than 1%. The QBER at 30% is less than 3%, and the secret key rates are 450 bits per second. This also depends upon how much is your input parameters. So far we have I have discussed about a constant link, right? So you have a constant loss and how much you get the numbers for the constant loss. But this is not the case in terms for the satellite, because satellite is not a constant object. It moves, and the distance between satellite and Earth is constantly changing. So you can consider an orbit which has a closest proximity to Earth at 500 kilometers. So at an elevation angle of close to 90 degrees. So this, you can see that the distances are changing, varies drastically over this 400 200 or 300 seconds or so. And the loss is also changing as a function of this distance. So losses are nothing but generally is dominated by the diffraction losses of the beam. So you can see that the loss is minimum at 0. That means at closest approaching point. So here, this is in the inverse loss in minus dB scale. That's why it's speaking. So since we have these losses, so correspondingly, you can calculate how much will be your Q-bar for a particular input parameters. Also, how much will be your shifted key rate. So since we have these values experimentally, we have all the loss values, and we have all these values shifted key rates for different losses. So we can stitch up all these bits and pieces of these shifted keys for with different Q-bar like this. So this is a simulation of a full pass. So here you can see that this is your Q-bar and this is your shifted key. So this is actually mimicking this plot, and this depends upon how fine you can change your loss. So we change our loss in steps of 1 dB, and this is how it looks like. And this has a parameter. Input parameters is 34 million counts per second. The source Q-bar is less than 1%. Average efficiency is 22.5 degree. 5%. Coincidence window is 1.5 nanoseconds. And once we have this, what we do is that we shuffle this. Once we have this shifted key, we shuffle this shifted key, and we measure the Q-bar. Once we measure the Q-bar, so the average Q-bar is 3.3% for the whole pass, because at each point the Q-bar is different, but the average Q-bar is only 3.3%. So once we have the Q-bar and once we have this shifted key, we can do an error correction, and we can get the total shifted keys. We got 26,000 bits per pass. That corresponds to more than 100 AES keys of 256 bits. Also, you can have finite keys, assuming the finite key length. We can have more than 13,000 bits per pass. That constitutes 56 AES keys. Some of the conclusions. So it's good to have a Ling model that predicts the performance under loss for a given system. Demonstration of we have done the demonstration of full QKD system using lab electronics and representative optical design. This validates our Ling model. This derives requirements and tolerances experimentally in a realistic satellite pass. In some settings, we get 100 AES keys per pass in asymptotic assumption. I would like to thank Tanvir, Aisha, Tom, and Alex for their contributions for software, Ling model, and optics. And thank you. And this is our group's website, and you can reach me at this email address. And if you have any questions, I'm happy to answer. Thank you.
All right, thank you, Chitra. That was very nice. So we'll, like I said, we will keep the questions for the panel discussion that will follow at the end of the first half. And so what we'd like to do now is actually to invite Daniel, our second speaker, to come up and share his slides. So Daniel and I have been collaborating for, I think, maybe 10 years or more now. And, you know, Daniel, I credit Daniel as the guy to first bring the idea of the nano satellite to my attention and said, hey, what can we do with this, you know, emerging technology from the satellite world? So we've been working with Daniel for 10 years, and you know, we published quite a number of interesting papers together, including the spooky one results. So today, Daniel's going to talk about another CubeSat QKD mission, the ROKS mission. So Daniel, please go ahead.
Thank you, Alex. Yes, thank you very much for inviting me to present our ROKS mission. This is an offshoot of another mission that I've been sort of leading in the UK. So I'm at the Super Department of Physics at the University of Strathclyde, located in Glasgow. I've been working with Alex, as he has said, for about a decade now, and I've been associated with the Centre for Quantum Technologies for even before it was established. So a really good lengthy collaboration with CQT. So today I will talk about, this is the talk outline. Basically, it's been a long journey to try to get CubeSat QKD up into orbit. And I will go through the various systems that we've been developing. Unfortunately, I'm not going to be able to cover quite a few bits, otherwise this talk would be way too long. So, so those things will probably, I may allude to them later, but I won't actually go into detail. So a prehistory of ROKS. Well, as Alex said, we've been working together. I first came to Arta Eckert in 2009 and suggested that we should be working on this. We should be using CubeSats, small satellites, to try to test quantum technologies in space. And we've been working for some time. And in 2014, Alex sort of prodded me to try to find out whether we could actually launch a mission or start developing launching a mission. And so thus began a long journey. We set up a consortium in 2015, which is called the CubeSat Quantum Communications Mission. And we got a pretty strong consortium spanning 6 nations, mainly within the European Union, but also including Singapore. And we came up with this mission concept, and we actually did quite a bit of work to show the feasibility of it. Unfortunately, that didn't quite go ahead, but it was very successful, and that it spawned many different other missions. So obviously, Spectre is one of those missions. This is the one between UK and Singapore. But in the UK, I set up the QARC, the Quantum Research CubeSat project, to try to take this forward within the UK. There are other missions which are following up. Now, ROKS, the ROKS mission, is an offshoot of QARC in that it sort of forks the technology and concepts developed within QARC into a commercial mission. So ROKS, it stands for Responsive Operations for Key Services. Now, this is to try to demonstrate that CubeSats can in fact perform quantum key distribution missions on a practical basis. And Craft Prospect is the company which is leading this mission. It was awarded a £1 million in-kind contribution towards launch and mission costs for a complete mission under the IOD6, the In-Orbit Demonstration 6 program run by the Satellite Applications Catapult. Now, ROKS forks basically the work done in QARC, which has had funding from the UK Space Agency and other places. But ROKS has also used a lot of other sub-projects and also developed various subsystems. So what I'm going to be talking about is primarily the more hardware and quantum physics side of the development. I won't be speaking very much about the other systems. We currently just finished the first engineering model phase, and the next is the flight model CDR, which should happen in mid 2021. So this is the system outline. I thank Chithrabhanu for basically showing a basic outline of how these systems work and the underlying concepts. So we've got a satellite here, which is a CubeSat. We've got our payload, which is sending optical signals down to the ground. So this is a downlink configuration. We've got beacons, which perform various tasks. And then on our ground station, we've got detectors both on classical optical channel, but also the quantum channel. We're going to be using 6U CubeSat. It's 90mm transmission aperture. For the purposes of a baseline configuration, we're actually going to use quite a small ground station, 432 millimeters. 100 megahertz BB84 weak current pulse decoy state, protocol. So this is a prepare and measure protocol, not entanglement. And we're using beacons. We've got rather modest pointing capability on our satellite, but we make up for that using a fine pointing system with 3 microradians pointing. We try to use as narrow divergence quantum beam as possible. Standard orbit, 500 kilometers, so it's sun synchronous orbit, noon to midnight. So this is the payload. This is the satellite and payload outline. So we're using the Open Cosmos 6U bus. And this is roughly how it's split up. 1 U for the telescope, the actual quantum source and the acquisition and pointing and tracking system, all the optics there is about 1.5 U. We've got systems for the star tracker and the platform itself. And we've also got an additional payload, which is a forward-looking imager, which helps look at AI and machine learning of cloud detection. And also it basically helps us do in-orbit scheduling of ground station transmission. This is a sort of system diagram. We've got platform systems at the top, and this is sort of a block diagram of how the various things work together. We've got a power detector. We have an alignment laser. So these are additional systems within the source to help us actually operate the system. So the heart of the system is the source. So this is a prepare and measure system. We're using laser diodes to produce the weak coherent pulse states. It's developed from an original system which was done by Bristol. They've been developing handheld QKD systems for many years. So they've got a lot of experience in building these very, very tiny transmitters. Most of this is just a 3D printed plastic part to hold an optical fiber in place. We've actually gone from this to an aluminium housing with discrete laser diodes instead of LEDs. And this is much higher brightness and should give us pretty good performance. This is the polarization performance, and this is in testing. This is the first generation driver board. We will be miniaturizing that to make it about the size of the actual source itself. Acquisition pointing and tracking system is very crucial in getting this 3 microradian fine pointing so that we can reduce the pointing losses. This is sort of the setup. We've got a fast steering mirror, which is a 5mm MEMS mirror made by Miracle. We have a beacon camera, which basically takes the incoming beacon light, determines a pointing offset, and then feeds back to the fast steering mirror to correct the offset. And we've got a fiber coupled source into a collimator, which basically aligns the outgoing beam with the incoming beacon beam up to the point head offset. We've got an in-orbit calibration system to make sure that we are always co-aligned with the beacon set point from the beacon camera. This is sort of what the engineering model of the APT system. So it's about half a U at the moment. We can shrink that out slightly. So we need to also be able to detect the beacon very sensitively. And so a lot of the work has been done to try to make the beacon system as efficient as possible, because we don't want to use too much downlink beacon power, but consequently, but also we don't want to have too much uplink beacon power. It makes things a bit easier to operate if we aren't shining many watts of laser light into the sky. So we've done a lot of work on the optimization of the uplink beacon system to try to reduce the amount of power actually required. So full analyses, simulations, and optimization of the centroiding algorithm has been performed to get down below 1 microradian centroiding determination, which goes into the pointing budget. So we've also looked at the design of the telescope. So the telescope is 1U, and it has fairly stringent requirements in terms of performance and also polarization maintenance. This is a geometric spot diagram of it. Obviously, you know, we can't get this geometric performance. We are restricted by the Airy diffraction disk, and this is you know, near diffraction limited performance up to the extremities of the field of view. So this is a Strehl ratio of about 0.997. Polarization has been optimized using the right coatings, and the ground spot size is you know, 11 meters full width half maximum at 500 kilometers. So so the actual loss we get from just from transmission is about 24.9 dB or 25.5 dB if referenced from the input of the telescope. On the ground, we're developing a portable ground station. So this is based on a plane wave CDK 400 system. This is a telescope. We have a separate uplink beacon, so we're not co-propagating with the downlink signal, just for ease of assembly. We have a beacon tracking system and polarization analysis unit and pulse timing system here, and we have a quantum receiver and a control system. So this is the actual test bed that we're actually building. This is the actual CDK 400 system that we have. It's a 17-inch reflector telescope on a alt-azimuth mount. We've got an optical breadboard at the back that we have designed a little system. We're using a flip mirror so that we can do star tracking and plate solve. We can flip it down and then we go into receive mode. We've got the beacon camera. We've got timing sync system, polarization detection module. And we have, this is the quantum detection module here. And we've got some polarization corrections systems. We've taken that into the field and done some field tests. We have a field test campaign coming up actually to test this with a quantum transmitter. And we've done some low Earth orbit satellite tracking tests to check that it can actually track low Earth orbit satellites. We get a course pointing over about 1 milliradian or less than that actually. And it's mainly in the long track direction. So it's mainly to do with timing errors. The TLEs that are given often can have a timing offset that is easily correctable. Thus, we could get the course pointing error well below 1 milliradian. The receiver itself, the quantum receiver, it's just a standard system that we've developed for the handheld QKD system, but we've adapted it for the satellite QKD system. Yeah, we haven't optimized the detectors themselves. We can improve what we have at the moment, but still, it's still performing quite well. We're using multi-mode fiber coupling from the collection optics into the actual detector unit. It's a modest amount of dark counts. Quantum efficiency is reasonable, but we can certainly get better modules to help. A key part is the timing and sync system. So because we're using a prepare and measure system, we can send the pulses out in well-defined pulse slots. So we just need to identify which pulse slot we got a count in and then send the number of that pulse slot rather than actual timing information itself. And so we want to convey the actual precise times of those pulse slots, as well as a system which allows us to do absolute pulse position numbering. So we've got a beacon system which allows us both to give us that very tight jitter to determine the actual coincidence window locations, but also we modulate the beam itself, the beacon, so that we can actually determine what the actual pulse number is. Now, the downlink beacon is actually steered with the quantum signal with fairly tight divergence, not as tight as the quantum signal itself, but still fairly tight, so we can reduce the actual power required. There is some margin so that even if the quantum beam does wander off slightly, that we still have a strong downlink beacon. So there's a 20 dB difference between the losses between the quantum and downlink beacon. We can get the average optical power way below 1 watt for the beacon. So to do the pulse positioning system, we use what's called a De Broglie code. This is the most efficient method of encoding a pulse position using a binary signal. And so we can very rapidly, within microseconds, determine exactly which pulse is being received to 40 bits pulse position. We've got an error correction and detection system so that we can rapidly reacquire the beacon position as well as correct for any errors. With the pulse detector itself, we've got 2 versions that we're evaluating. We've got a conventional APD, and we've got a high performance APD, which is used for automotive LiDAR applications. So we're evaluating that to try to get the power that is required to be detected by the beacon sensor much lower. We can achieve a roughly 100 picosecond jitter with the current system with representative losses in the orbit at maximum range. Now, as was mentioned in the previous talk, the analysis of how much key that you can actually derive from a satellite overpass is very important. So we've been doing some preliminary analysis. We've been doing using the asymmetric BB84 decoy state protocol with 3 intensities or 2 decoy states. And we optimize the state intensities probabilities and basis encoding probabilities in order to maximize the total key length that can be derived in a single pass. We do this in the finite block size scenario. So we take the entire signal that we collect on the ground. We optimize how much of that signal we actually will process in a block, and then we can work out as a function of the sort of the transmission loss how much key can we get. So here is the total system loss. This doesn't include the actual detector loss, but so 32 dB is where we're operating at the moment. This is reference to the loss at zenith. So obviously the losses are greater as you go down towards the horizon, but this is just a good reference point. And you can see that we can withstand up to about an additional 4 dB roughly, depending on the dark count and the intrinsic polarization quality of the source. So we've got some margin for a zenith pass at least in order to generate quite a lot of keys. So here, this is 1 million keys at this point. So we've done some modeling with various qualities of the source itself. The current source is it's in the sort of several percent. Well, it's about 1 or 2% probably at the moment, but we can improve that, and we hope to get to at least 1% or ideally about 0.5% or 0.5% with some improvements to the component selection. If a single pass is not sufficient to generate a key under finite block size assumptions, we can go from a 0 to a non-zero key just by adding a few extra passes. So if we're operating at this point, say, so 36.2 dB system loss, even with a 0.5% error on our source, with 10 to the minus 7 dark count per pulse, we get 0 key in a single zenith pass. But if you just add 1 more pass, you can actually go from 0 up to over 1 million bits per pass on average. So this is actually nearly 3 million bits for the 2 passes. And this ratio, this efficiency goes up as the more passes you take, obviously. And we've looked at what happens, how far we can extend the acceptable loss in the channel as a function of number of passes, and we can extend it, roughly, so 3 passes, we get improvement of about 0.9, 0.8, about 0.8 dB. So, if we increase the number of passes, we can increase the tolerance to loss in the system. Obviously, this is a preliminary analysis. We need to do non-zenith passes. We need to do long-term orbital simulations to see, like for instance, over a year, how much key we can generate. We need better estimations of the leakage and the reconciliation process. We need more accurate models for turbulence and atmospheric absorption. And we would like to explore the whole system parameter space to try to optimize the whole system. We can certainly use larger OGSs. So at that moment, we're looking at the very small OGS, but we can certainly we can increase that by about 6 dB just by going to a standard, sort of 1 meter class receiver. So future work, we're going towards the CDR for the flight model. We need to redesign the back-end optics of the OGS to reduce its size and lower the dark count rate. We want to put the OGS on a mobile platform. So this is some sort of concept that Nissan and the European Space Agency came up for a portable observatory. So something like this is what we envisage. we need to make sure that the fast steering mirror can survive launch and operation in space. We are going to go through a ruggedization process for that. Already done some preliminary environmental testing, thermal vacuum testing of that mirror. We've started some thermal and mechanical analysis, but that needs to be improved. We're getting a telescope designed by Fraunhofer in the UK. New driver boards to increase the transmit rate and control over the intensities, and a whole bunch of improvements. Beyond ROKS, we would like to go to really high rates towards a gigahertz rep rate, with division, a dense wavelength division multiplexing, reduce the size of the OGS, perhaps go to adaptive optics and single mode fiber coupling. This will help for instance, daylight operation. And we might be able to miniaturize the whole system down to a 3U platform. And obviously different sources should be compatible with the system that we've actually built, since it's easily fiber coupled. And so this is ROKS team. It's a lot of people. I'm a theorist embedded in the physics department, but we involve experimentalists down in Bristol. We have space engineers, which have done a lot of the orbital analysis and platform analysis. Craft Prospect is driving the ROKS project, and a whole bunch of really good engineers there, some software development, and some former members, some of which have escaped to NASA. So, there's been a very good team behind me. Anyway, so that's all. Thank you very much for listening, and I'll happy to discuss this in the discussion session.
Thank you, Daniel. That's a very nice overview of the ROKS system. Now, so far, our first two speakers have been talking really about point-to-point communications. If we want to extend beyond that and, talk about building a real network or internet of some kind, we're going to need, atomic systems in space acting as quantum memories. And that's where our third speaker will have something to say about that. Mustafa?
Hi, can you hear me?
Yes, so if you're ready.
Okay. Yes, I can share my screen.
Mm-hmm.
Here it is.
Sorry.
This is all right? So yeah. Can I start?
Go ahead.
Yeah, thanks, Alex, for the invitation and for the organization. And my name is Mustafa Gündoğan, and I'm part of the joint lab integrated quantum sensors based at the Humboldt-Universität and Ferdinand-Braun-Institut in Berlin, led by Markus Krutzik, and we have strong collaborations with just the previous speaker, Daniel Oy. So this is the short outline of our group's research interests. So we are basically trying to come up with solutions to problems in the domains of these fields and applications, basically. And then these are our diverse research activities. And then my research lies here, basically. So atomic physics in space for quantum communication applications. So I will start off by short outline of what quantum memories are, right? Before going more deeper. So the main goal of these devices is to store the quantum state of an input photon and then read it out on demand at a later time. So this on-demand functionality is quite important. And then they are mainly used as, or planned to be used as interfaces between flying qubits, right, used for quantum communication, and matter qubits used for either processing of this quantum information or storage. And then they are needed in many complex protocols that involve several probabilistic processes that need to be synchronized. For example, photon creation, processing, or Bell state measurement. And it is within this context that memories are useful for quantum communication. And quantum communication, I mean, we already saw two talks on the topic, but still, the transfer of a quantum state between two or more parties, and usually photons are used, different degrees of freedoms of photons are used, but the loss in optical fibers limits this transmission range, right? So that's why we want to go to space. And as a dramatic example to show how dramatic this loss is, so if you start with a 10 gigahertz repetition rate, single photon source at the telecom wavelength, so it would take you more than 300 years to get a single photon across 1,000 kilometers distance. So this is really, really bad. And in classical domain, in the classical world, optical repeaters can be used to amplify the signal. However, in quantum mechanics, this is forbidden by the no cloning theorem. But one solution to this problem is quantum repeaters, and then the other is space-based QKD to go to space, as we said. And again, a short outline of repeaters this time. So the idea is to divide the whole communication length into 2 to the n smaller segments, and here n is the nesting level, and then each smaller segment length is L0 here, and then create entanglement between the neighboring nodes, and then store this entanglement or the entangled state in the local stations until the other entanglement generation attempts work. Then once you are sure that all the smaller segments are entangled, then you perform a Bell state measurement on these two memories to perform entanglement swapping to extend the entanglement over the whole range. And then here, these boxes represent entangled photon sources, photon pairs, and memories. But the problem with land-based or ground-based repeaters is that even the longest range ground-based quantum repeater architectures has a predicted range of well below 10,000 kilometers. So they are quite applicable between different cities, for example, but for truly global distances, land-based repeaters fall short of expectations. And this problem was already known. And already in 2015, a protocol, a hybrid protocol based on satellites carrying photon pair sources in space and memories in ground stations was proposed. And here the idea was to replace the exponential fiber loss with the polynomial free space loss. And now with this, it was shown that global distances is now within reach. However, the problem or the disadvantages of this scheme is that the weather in all ground stations has to be simultaneously favorable. And as the nesting level increases, the number of ground stations increases as well dramatically. So for example, nesting level of 3, you have 9 ground stations. And then the space to ground losses here are still higher than space to space losses. So if you can bypass these connections, because they eventually go through the atmosphere, and if you can establish these links totally in space, then it will be a better option, of course. And at the time of this proposal, it was thought that the memories, quantum memories based on atomic physics experiments were difficult to operate in space, but we will show that actually this is not the case. And then as an example for the weather, so if you assume that the average good weather probability for a single station is 70%, then for all 9 stations, the probability that the weather would be good at all stations is half. And then you see how dramatic it changes. So 1/3 of a chance for a good weather for a single station, then it's almost, it's practically impossible to have good weather in all stations. And then here I give a short break to summarize the recent developments in atomic physics in space, right? And so in 2018, so the first Bose-Einstein condensate was created in space. And then at the same year, we see the results of the atomic clock based on laser-cooled rubidium atoms being published. So this was demonstrated on board Tiangong, I think, to space station. And then this year, we saw the result of the Bose-Einstein condensate continuously being operated on the ISS. And then we will actually hear by the author today. And in addition to these works, a huge effort is now being directed towards miniaturizing quantum memories and laser systems in ground, basically quantum optical components, miniaturization of quantum optical components. And then these two frontiers, in the end, pushed us to reevaluate the the global repeater scheme with satellites. So this was the original protocol. So you have the satellites carrying the entangled photon pair sources, and then you perform the entanglement swapping operations in ground stations. And then here, as we said, the total ground stations is this. And however, so in our case, we basically put this station, the ground station, all the components in this ground station in a different satellite in between photon pair sources. And then now we will see the performances that this scheme will offer us. So the entanglement distribution time with this protocol is given by this relationship that depends on the source repetition rate and the source detection, quantum non-dilution, and memory and detection efficiencies, and of course the channel average 2-photon transmission. This is the channel length, channel loss, and then the nesting level. So we start by comparing or calculating the scenario that includes a well-known repeater protocol called Duan-Lukin-Sirac-Zoller that was proposed in 2001. So here, this is what you see. So if you assume all memories in space, only two ground stations, and this is what you get with this well-known protocol with single mode memories, and it takes more than a day to distribute entanglement across the whole globe, across 20,000 kilometers. And if you use multimode memories, here what I mean by multimode memory is, so the memory should be able to store 100 consecutive pulses before releasing any of them. So like a pulse train of 100 signals, basically. And then, yes, it gets better. And this is the hybrid ground space QND protocol that I summarized and which was proposed in 2015. So again, so across the whole globe, it's around like an hour, basically, to distribute one entangled pair. And but then if you now put the memories in space with these parameters, then you can reach entanglement. You can reach to around like 1 second of entanglement distribution time across the whole globe. And yes, and then we have almost 3 orders of magnitude higher key rates across the globe. And then if we look at the different memory efficiencies, because so this calculation assumes quite a high memory efficiency of 90%. So what if you have a non-perfect memory? So here we see that actually the effect of the memory efficiency is quite dramatic. So already with 50% efficiency, you go down by factor 2 orders of magnitude lower values. Then it takes almost a minute to distribute entanglement across, again, the same distance. And then given that the satellites have in low Earth orbits flyover times of around a minute, so this makes it almost impractical to get reasonable key rates. So this shows us that actually you have to have super highly efficient memories. And then likewise, if we look at what happens with different beam divergences, because again here in these calculations we assume 5 microrad of beam divergence, which is here, right? We were here, and going towards diffraction limits would help us again by pushing the key rate to almost 2 orders of magnitude. And then here the lower end is a diffraction limited beam, what you would get with a diffraction limited beam, and the higher end of this plot shows you the divergence achieved at the on the Michiel satellite. And so this was the use of quantum memories for global communication, right, in a network setting. And but we also calculated the use of memories in a line of sight setting in the context of memory assisted QKD, in a memory assisted QKD fashion. So here in this plot, so we first calculated the QKD key rates, and with no memory and with a repetition rate of 20 megahertz, and then all the rest, the other parameters are shown here. And so in the downlink configuration, if you have a single mode memory with a 7.5 seconds of storage time, you are far below this no memory threshold. But if you use now 1000 temporal mode quantum memories, again with the same storage time, then you beat the no memory case up to almost 1400 kilometers. And but then there was a recent modification of this protocol that basically includes not a single pair of memories, but a high number of memories. In this case, for example, we put 100 pairs of memories in the ground station, and then this basically relaxes the requirement on the storage time. So so to get a similar performance, now you have to have a memory time of around 100 milliseconds, down from 7.5 seconds. But on the other hand, if you use the uplink configuration, then the required storage time is far shorter, which is now 25 milliseconds. And the main reason is that in this configuration, the end part, so you don't have to communicate the measurement results classically to the middle station, whereas in the downlink configuration, this is something you have to do. So, and then that basically limits the key rates. And then with this, I already am coming to the conclusions. So our main motivation was realizing that like reaching global distances is difficult even with land-based repeaters, quantum repeaters. And in the recent years, as we will also see in the second part of this workshop, atomic physics experiments in space are now within the realm of possibility. So they are no longer a dream, as we thought maybe a decade ago, at least the quantum information people. So we extended the earlier space-ground repeater schemes, and we demonstrated that the space-only repeaters offer way faster entanglement distribution times across the whole globe. And I should also note a similar work published or uploaded archive recently. And then we quantified, moreover, the advantage that memories would bring in a memory-assisted QKD fashion within the line of sight setting. And then with this, our main message is that quantum memories will be highly crucial to go beyond the trusted nodes paradigm towards untrusted global space quantum networks. And our outlook is, so within our lab, so we now started setting up an cold atom-based experiment, memory experiment, and with all the heritage of our lab. So we will try to create a miniaturized and rugged memory experiment for space. And then I should acknowledge our collaborators and funding agencies. So Markus, Victoria, so we are based on, and myself at Humboldt, and we have all these fantastic collaborators. And with this, I would like to thank you.
Thank you, Mustafa. I think that was also a wonderful talk about what we can look forward to when we get this quantum memory into space. Now, I'd like to, invite Daniel and Chitra back onto the panel. And we can actually now, start by having some questions from the floor. So if anyone has any questions, there's an option here where you can actually just type it into the chat, right? And then we'll read it off. So we can actually let everybody see your question. Or if you want to speak up, just feel free to say something. So I'm going to just kick off while you guys are thinking of questions to ask everyone. I guess one of the questions I had for Daniel was, in the ROKS system, you had this very interesting camera that's attached to the payload as well. You said that this was to help you schedule ground operations, and you had some kind of AI, involved, and it looks at the clouds. Could you actually discuss that a little bit? Just comment on that system. Daniel, you are still muted.
So this system, it's developed by Craft Prospect, and the idea is that they use onboard AI and machine learning algorithms to identify cloud cover over the area of interest prior to actually coming up for a natural pass. It could be used in a constellation, for instance, where you had multiple satellites and they would scan areas, so you could then inform other satellites which are coming up over later on. This has been developed as a product by Craft Prospect, obviously not only for QKD, but there could be other applications, for instance, classical optical communications, but also other applications where some sort of rapid response in orbit processing of the data could be very useful. I'm not directly involved in this part of the project, so I can't really say too much more about the details.
Right, but I have just a curious question about how one would actually use this capability in a single satellite for QKD, because obviously as you fly over the ground station in a SSO type orbit, you would first approach at an angle over the horizon, then maybe over zenith, and then over again at another angle. So at the first pass, you probably would be scanning the ground station, but then you'll be trying to predict what will happen 19 minutes later.
Yeah, so if you have many different ground stations, so for instance, if you want to try to schedule, which ground station to talk to, you could possibly, at least have some estimate of what the weather would be like at particular places, and try to do some sort of assessment of that. I'm not quite sure exactly how they anticipate using it, but these are things I think will be worked out when a full constellation of, I don't know how they're going to use it in a single satellite situation, but as you say, we do need most of the pass really to do the actual transmission. So we're still working on the exact overpass key length relationship. So you could probably get away with perhaps a smaller segment of the pass, and so give you at least tens of seconds or maybe 100 seconds of prior warning, maybe.
Okay, all right. Thanks, Dan. I see Paul has appeared on the screen, so I assume he wants to ask a question. So go ahead, Paul.
Yeah, I do have a question for Chithrabhanu. So I think you said, I wasn't quite sure I got it, but I think you said that the secret key rate depends on the coincidence time window that you're using. Presumably because this is a CW source, and also depends on the loss. Obviously, that's got to be true. So the question is whether or not when you're trying to get your optimal key per pass, you should be changing the coincidence time window as the satellite is going overhead, because the loss is actually changing. So presumably the optimal window that you use can change, and that's the thing you could presumably change. That would be easy enough to change in real time. Might not be that easy to change your source parameters in real time, but I guess you could change the coincidence window.
Possibly yes, because the coincidence window, what we in these models, we use a fixed coincidence window for the whole pass. But this is possibly a possibility that you can change the coincidence window for the higher losses. That's true.
I guess it'd be interesting to see how much of a gain that gets you. Probably, and my guess would be 20 or 30%, not huge factors.
True. Yeah, we'll look forward to check that. That's a good suggestion. Yeah.
Okay, Paul, will you have any other questions for our other panelists?
Not yet. I wanted to see what other people were going to ask.
Okay. Well, I think we've got some questions on the chat. So let me just read out some of them. So from Avik Chandra, there's a question here. It says, atomic quantum memories have a smaller storage time on the order of milliseconds or tens of milliseconds. Do you think it will be enough to implement quantum repeaters over long distances, be it satellite to satellite or satellite to ground? So I guess this is a question for Mustafa.
Yes, so this is a good question, but it's actually not quite true that the memories are limited to some milliseconds. So in the last couple of years, so there have been quite a big, impressive improvement of the memory performances. And I can count, for example, 3 examples. So I think last year or 2 years ago, Ofer Fürstenberg's lab at Weizmann, they demonstrated storage of classical light pulses up to 1 second with warm vapors. So this is one. And then with cold atoms, already in 2013, Alex Kuzmich's lab demonstrated, I think, almost a minute, like 15 or 16 seconds storage time. And with rare earth doped crystals, you can go even higher to minutes. And there's a potential of going to even hours with European doped rare earth materials. So the possibility is there. I mean, single photon level storage at this long storage times have not been performed. So all these experiments that I quoted right now, so they were realized with classical pulses, but it is a matter of filtering, let's say, frequency and spectral filtering, which is technically quite difficult, this I admit, but the capability is there.
Okay, thanks, Mustafa.
Mm-hmm.
Now we have another question from Adria Sansaperna for Chitra. So which model or reference papers have you used to calculate the key rates?
The constant link key rate model is basically from the first principles. We assume the rates, and we assume how much is your detection efficiency and your source parameters from the first principles itself. You can derive how much. I didn't have the time for that to explain that. I had some backup slides, but you can contact me. We can have a chat about that. On the other hand, if you choose the link model, the dynamic link model, you have to assume some basic Gaussian optics that also straightforward. For the finite key analysis, I have already given the citation for that.
Okay, thanks, Chitra. So Christoph has a question for Daniel. And he says, Christoph is asking, can you briefly explain the procedure of how you synchronize the receiver and transmitter for the pulse position modulation scheme?
Yeah, so I'll just share my screen for the moment. So this is the step that we use here. We've got a beacon which is pulsed. We're playing between 1 kilohertz and 1 megahertz. The quantum signal is 100 megahertz. So there's many quantum signals per beacon. So the leading edge of the beacon gives us this 100 picosecond jitter time signal. Then we interpolate the intermediate pulse positions for the quantum signal, and there's an interleaved De Broglie modulation code. So every second pulse is either on or off, and depending on that code, we only need about 30 beacon pulses in order to determine exactly which beacon pulse number is to up to 2 to the 30. And so that we can then use that to then determine which beacon frame and which beacon pulse position that we made a detection on the ground, and then just tell that number to the satellite for sifting purposes. So there's no need for actually doing any time transfer of time. We do everything in software. So we do time stamping of each of the beacon pulses of each of the quantum detection events, and then we just do all the sifting in software, and then we can then send that up, that information up.
Thanks a lot, Daniel.
Hey, thanks, Daniel. So Paul actually has a question. So Paul, why don't you just go ahead and ask?
Great. So sorry, this is also about the quantum memories. So many of the plots were showing and assuming that there's either a QND measurement in front of your quantum memory, which I know obviously that helps because you know that your photon made it, or equivalently or implicitly that there's a heralding quantum memory that just tells you that something made it in memory. The question is, if you don't have that, is there, what kind of benefits are there? And maybe the alternative question is, can you get that out of these Because I know many of the quantum memories don't actually give you that sort of feature.
Yeah, exactly. That's right. I think the other alternative is, instead of quantum non-dilution measurement, that so you have the single photon arriving on the memory, right? And then to herald this, then this input photon should have another pair to herald the presence of the signal carrying photon. And then this would bring up additional layer of complexity. So I think this is a matter of taste, let's say, for the experimentalist, and the technical difficulty, whether you prefer these additional layers of extra photon pair sources for heralding or quantum non-dilution measurements. This is my view on it. And for a repeater protocol that doesn't rely on QND measurement, so for, I think, the single photon or the repeater protocols that rely on single photon detections, so you need to have a phase stability across the whole link, but you can get rid of this phase stability by two photon coincidences, or using repeater schemes that rely on two photon coincidences. But I checked them actually during while writing up the paper. So with two photon repeaters, the count rate is less than one photon. Exactly. Of course, I mean, that's so it's a matter of like which technologies further, and this is my view. So QND is technically challenging, but the others are also quite challenging.
Great, thank you.
Yeah, thank you for the question.
Okay, and then we have a question from Bhaskar for Chitra. It says, Chitra, you mentioned that in the source, it can tune the rate of page generation and go beyond 50 megahertz. If it is by tuning laser power, how do you take care of multi-photon pair events?
Yeah, basically multi-photon pair events will end up as extra qubit in your system. But on the other hand, you have the signal downlink is heavily lost. So it's adds like another qubit only.
Okay, thanks, Chitra. Now, Tobias Vogel has a question for Mustafa. The question is, you have shown satellite to ground and satellite to satellite links. Could you comment on the pointing accuracy and transmission efficiency for both scenarios? For example, for the satellite to satellite link, you don't have the advantage of a large telescope in the ground station.
That's right, but for the ground stations, I assume the half a meter wide telescope radius, which is kind of large. I think this is what the Mish's ground stations have, if I remember correctly. But for space-based scenarios, I also assume the similar red eye. And then again, as a theory or a calculation paper, we relied on the future, let's say, foldable optics type of new generation space telescopes. So this is what one might expect in the future for development. And then for the second part of the question, so we expect, so in all these calculations, I didn't include the tracking and pointing accuracies. I set everything to, I mean, those parts to unity, basically. But for in real life, one might expect better tracking for space-to-space links, because the satellites' relative position with respect to each other don't change, right? So then you can compensate for such stability in space, basically, because otherwise you have to compensate for 9, like more than 10 maybe ground to space links simultaneously, which is, I think, more difficult than keeping constant distances in space.
Okay, thank you. So I guess I'd like to just take one more question from the chat, and then we'd like to end here so that we can actually all have a few minutes break before we reconvene at the half hour for the second part of the workshop. So our last question is from Alex to Daniel. It says, a question regarding the synchronization procedure. How robust is it to missed pulses?
Yeah, so we're actually quite robust. So we've done simulations where we put in quite a high error rate, and then we try to use our error decoding error detection and compensation and correction scheme. And so we've done simulations with quite high error ratios or missed pulses. And one really good property of the Bruin code is that you can very, very rapidly pick up your pulse position counting once the signal, once the channel resumes. So yeah, within 30 beacon pulses, you now get your pulse position back. And because everything's done sort of in software and with time tags, you can actually go back in time. So this can all be done sort of semi-offline. And you can go back and do your more sophisticated reconstruction techniques. And because the Bruin code is deterministic, then you can always count along. And so if you ever miss a couple of pulses, as long as your clock stability is good enough, you can compensate and actually sort of interpolate over those missed beacon pulses.
Okay, thank you, Daniel. So I would suggest that we all can take a break now, and we'll come back on the half hour for the second part. And thanks everyone for the the questions and engaging with the panelists. All right, I'll see you guys in a few minutes.